Okay, good afternoon, everyone, and welcome to the B. Thomas Golisano College of Computing and Information Sciences and the Dean's Lecture Series. My name is Andrew Sears. I'm the Dean of the College, and it's my pleasure to introduce our speaker today. The purpose of this lecture series, which has been around for about 10 years now, is to bring talented and insightful individuals from industry and academia and government to campus to share their insights with our faculty, with our students, and with the community at large. And I believe this is the 46th speaker in this series. And today, it's my pleasure to introduce Dr. Gary McGraw. Gary is a globally recognized authority on software security and is the Chief Technology Officer at Cigital. I got it right?
You got it right.
We were talking about that earlier. A leading software security firm that is headquartered in the Washington, D.C. area. In addition, he's the author of 8 best-selling books, including Building Secure Software, and a strategic advisor to quite a few IT executives. In today's lecture, Bug Parades, Zombies, and Building Security and Maturity Models, a Decade of Software Security. You got a long title.
That's a long title.
Gary will take us on a journey through the last decade of developments in the area of software security, and we'll talk about how we've moved really from very much of an art to more of a measurable science, and kind of talk about how far we've come and the steps that we have left to take. And without any further delay, it's my pleasure to introduce our speaker, Gary.
Thanks. Hi. Hi. Oh, good. Everybody's awake. It's the coveted after-lunch speaking slot. It's always everyone's favorite. Let me tell you where I'm coming from so you know what we're going to do. The dean just said exactly kind of what I'm going to talk about, so that's good. My company called Cigital does software security all day, and that's all that we do. So if you don't know what software security is yet, by the end of the talk, you oughta. But what I want to let you know is I'm not going to talk about theory. I'm not going to talk about, possibility space. I'm going to actually tell you about what we do on planet Earth to make software secure for huge software companies and huge multinational banks. At the end of this, I want to start at the beginning and sort of give you my view of a decade of this stuff. But at the end, I want to show you kind of a way we've come up with to measure software security. Just so you know, though, this is all stuff that's based on experience over the last 15 years or so doing software security. I got started in this field myself in 1996 when this language called Java came out. Anybody heard of Java in here? Yeah, so you might remember that there were some people who were breaking Java a lot back in the mid-90s. Well, that was me and Ed Felton from Princeton. And we wrote this book, which is hidden behind this unimportant book, this really important book back here. And it was really about how the Java virtual machine was busted and ways to fix it. And the question that it brought to mind for me after doing it for a few years was, why were these amazing guys like Guy Steele, who's probably the best programming languages person on the planet, or Bill Joy, who's no slouch, he wrote Berkeley Unix, among other things, why did they screw it all up when it came to security? And if you were not a super wizard, but you were just sort of a mere mortal, how would you not screw it up when it came to security? And more importantly, where would you go to learn any of that crap? The answer around 2000 was nowhere. There were a couple of books. There were a couple of papers. There was a paper called Smashing the Stack for Fun and Profit that Alf One wrote. There was a paper called Bishop and Dilger's Talk to Time of Check to Time of Use stuff. But really, that was about it back then. So I wrote this book with John Viega called Building Secure Software in 2001. And it's been, I guess, 11 years since that book was published. And things have changed a lot in those 11 years. Now there are plenty of places to look. We actually know how to do software security. We're beginning to understand how to measure some aspects of software security, and that's really what I'm gonna talk about today in the talk. So let's go back to the beginning of time. In the beginning of time, pictures were black and white, and they didn't have bits, right? And people had funny-looking hairdos like that. So you used to have computers that were a room, and you would walk into the room, and there were certain high priests of computer land that were allowed to walk in the room, and everybody else had to genuflect in front of the little tiny window, right? And so what you would do is you had your punch cards. There's some genuflectors in here, I can tell. You, you had your punch cards, which you had neither folded, spindled, or mutilated, and you brought them to the window, and you sort of bowed to the high priest and say, would you please run this eventually, right? And so they would take it in, and they would schedule it for 3 days later, and there would be a bug, and you'd get it back, and they'd go, never bring us a thing with a bug again, right? By the way, the next cycles are in 7 weeks, right? So people were a little more careful with their code, and it was pretty easy to secure the computer because, you know, the only way in was through that little window. And the only code that ran was the code that was on those punch cards that those guys ran, and usually one thing ran at a time. Well, IBM fixed all that. I guess in around the late 60s, they unbundled the computer software and the computer hardware and started selling things differently so the hardware could have multiple software possibilities and you could change what the thing did. Although, you know, for the most part, the computers were still in the room. What happened with the computer room was people started running wires out of the room, and the wires made it all the way to the terminal room next door, so 20 feet, right? And there were a bunch of dumb terminals connected into the mainframe. The dumb terminals were like VT100s and ADM5s, and you might remember that. You know, remember how to do a bell on an ADM5 or a VT100? It's Control-G. You can still send a Control-G to a browser, by the way, and it'll bing, which is ridiculous, but it still does it. Right, so what happened was the high priest of computers lost track of what exactly was running because we had multiple users on terminals. Now, we still could keep our eye on them, and we could still make them log in, and basically the wires only went about 25 feet or so. So security wasn't really impossible, but it was beginning to get worse because the situation was actually beginning to get geographically distributed, and this was before the net really caught on, and you know, then there was the internet, and then it was big trouble. So let's fast forward all the way to now. Now, in a lot of corporations, you have this problem in computer security. You've got the people that write code that really needs to be secure who may not be doing it right, the super rad developer dudes, and you have the poor network security people who are supposed to be doing security for the whole entire system. So you go over to the computer security guys and you go, all right, you guys, what about software security? And they go, yeah, software. We hate those developer people, you know? We have a perfect computer, everything's all set up, the network's all great. If it weren't for the users, it would be awesome. And the worst users of all are the users with compilers over there. So why don't you go talk to them? So you go over here and you talk to the people in software land and you go, hey, what do you guys know about security? Are you thinking about security while you're creating all that software? And they go, yeah, security, I think those guys are over there. They live in the basement. Yeah, they don't get much sun. And I think we hate those guys. They take away our privileges. We can't even run a compiler. They won't let us do anything. They run antivirus and slow our machine down and eat all those cycles for my really wonderfully tight code. And, could you just take care of those guys for me? This was the state of the practice about the mid-90s. So here in the middle was who? It says it on the slide in red. Nobody. So, right. Who was getting software security done? Nobody. And who was getting fired when it failed? Nobody. Who was getting a huge bonus when everything went peachy keen in software security? CEOs, that's right. Trick answer. There's always one. Right, so really we've made some progress since then, but the first question to ask yourself as a firm is whether anybody actually has the job of doing software security. If you work for a company and you ask who's in charge of software security and the answer is nobody, don't be surprised when that's who's getting the job done, right? And they're not doing anything. So Management 101 dictates that you identify somebody and you give them both authority and responsibility and maybe some resources to get that thing done. Now we're at that state, but it's taken us a long way to get there, and we've got all sorts of problems. So I want to try to give you a very quick history through the bug parade. The bug parade is important because, in the commercial world, there's this massive overemphasis on bugs in software security, sometimes called application security. So you might have heard of say, the OWASP top 10. Who's heard of that around here? Some nods, yeah. Yeah, well, the top 10 according to what criterion? Do you guys know? Well, it was like some guys sat around drinking beer, and they're like, well, I think SQL injection. All right, that's cool. Well, how about like cross-site request forgery, dude? Oh, yeah, that's important. Well, how many do we have? 2. Okay, think of some more. So you might think, sorry, that's the way it really worked. So you might think that, the bug of the day is like the most important thing, and if we only eradicated that bug, it would be great, but that's just a bunch of hocus pocus. And to make clear how hocusy pocusy is, think of the first bug in the bug parade, the dreaded buffer overflow from long, long ago in the Wayback Machine. Let's look at some code real quick. Here is a declaration of an array, and then in a little thing, we're setting the 12th thing in the array to 0. What's wrong with that code? Quick. There's no 12th thing. There are 12 things. Look, right there. There are 12 things. Yeah. And I'm setting the 12th. Right? Yeah. Well, in C, we start with 0. Why? Because no other humans do that. Right? Who has a 2-year-old? You're like, okay, kids, start counting. No, zeros first. No, zeros first. Yeah, I didn't think so. So why would you start with 0? Well, there's a perfectly legitimate reason for that. Anybody know what it is? Yeah, it's offsets. You start with the address, and you got an offset times, you multiply the offset times that thingy there, and you get 0 times that, 0, so you start with the first address. Wow, that's great. So it makes it more convenient for the computer, because the computer's more important than the human. Right. That's no longer the case, right? So now computers are cheap. They're almost free. In fact, net seems to be free, and disk space is free. About the only thing that's not free now is the people who run the machines, but the ones at Google are better than us, so we'll just let them do it, right? But we wonder why there are a million problems in C. One of the issues is silly things like this. Offset makes sense if you're a deep geek, but it's a really crazy way to think about it if you're just coming at this fresh. Who the hell starts with 0, right? Oh. So if you look at the dreaded buffer overflow over time, this was a little bit of data that was first captured by David Wagner, who's at Berkeley now. And I remember David gave his first talk at ISOC NDSS in maybe '97. He was a nervous wreck, and now he's like a super amazing guy. So he did a calculation of the number of major CERT alerts, which at the time were the most important bugs because they were bugs that were being found all over the place in all sorts of installed bases that needed to be fixed and patched. And how many of those were buffer overflows? And the answer was about half. So that was a good reason to stick that on the bug parade. And in fact, we still have all sorts of problems that are caused by C. In fact, C is bad. Let's all say it. You ready? C is bad. Now, one more time. He's not going to say it. Let's make him say it. Here we go. Ready? C is bad. No. There are 2. It's the first 2 rows are problematic. So I once gave this talk at AT&T Research, and Dennis Ritchie was there before he died. I guess it was 2 years ago or last year. And I used to get everybody to chant, C is bad, and nobody would do it until Dennis kind of went. And then everybody's like, C is bad, which was pretty funny. But I have another Kernighan and Ritchie story. It's about Brian, and we did a workshop in 2003 where we got all of the software security people in the whole world together, and there were like 25 of us, right? So everybody got together, and Kernighan gave a great talk about beautiful code and trying to do high reliability stuff and how you do that, how he did the phone switch code and so on. And at the end of the talk, there was some smart-ass person from software security who goes, yeah, that's a great talk about the beautiful code and all that stuff, but I just got one question for you. And Brian said, yeah, what is it? He says, well, what's up with those string handling functions anyway? You know what Brian said? He didn't even slow down. He goes, yeah, that was Dennis's code. And really, that's what he really said. So if you want to know the problem in software security, you got it right there in a nutshell, right? So we started with some obscure stuff, and we blame all the bugs on the other guy. And there you have it. So we teach everybody who learns how to code in C on chapter 7 of the Bible on page 164. We have this function called getS, which is a total disaster. Like, why the hell is that still in the language? What does getS do? It gets a string until the attacker decides to stop sending you data, which means your buffer ain't big enough, right? And it can be worse. We can stick getS up here in, we declare a buffer locally. Where's that buffer going to be stuck? On the stack. Superb. So we stick a buffer on the stack that's only 1K big, and then we get as much input as we want from the attacker. And when you do a clever buffer overflow attack, the idea is to overwrite the return address on the stack frame so that you point back to your own self and you execute some code of your own, right? So you can build a tight little thing, and then you can take control flow over, and all of a sudden you have the privilege of whatever process happened to be running when it did that buffer overflow. That's bad. It's very bad. And there are a lot of those. So this was an early bug. And sadly, in C, there are a whole bunch of these things. There are a whole ton of things that you have to avoid when you're writing C code. And in C++, that's even worse. That's the worst language ever voiced on planet Earth. Truly, horrendously bad. It's horrible. And we should stop using it. That would help security a lot. But we can't. So instead, when we review code that's written in C or C++, we have to remember all of this stuff. At the same time, we're trying to figure out what that person that wrote the code was thinking. Like, whoa, who's done a ton of code review in here? Who's ever done a multi-million line code review code? We got one right here. So, was it really fun? No. Exciting? No. The two people agree that no. So here's how you do it when you're doing code review. You're really diligent at first. You sit down with the code and you go, wow, I'm going to check all the includes and the if-defs, and I'm going to check all the hash defines, and everything's going to be great. And then you get to the first line of code, and you go, yep, there's main, and here we go, or that variable's declared over here, and you're very diligent until you get to page 2. And then you go, that looks like a bunch of functions. Some curly braces, that's good. Oh, there's a curly brace, yep. Then you get to page 3, and you're like, well, that's code too. In fact, it all looks like code from here on out. Okay, I'm done. Anybody ever do that? You didn't do that. Yeah, that's how code review works. So when things are tedious and boring, and, they take a lot of keeping track of all sorts of stuff, what do we generally do as a species to solve that problem? Ignore it. Bad people in the middle. No, we have a computer do that, right? A computer can do that. So we can invent some static analysis technology to look for some of these problems and debug our code for us. And, we've come a long way with static analysis technology, and that's good. But really, what we might want to do is just ban C. Really, it might be better. Or maybe there should be a test, like a driver's license, right? So you take a test, and if you pass the test, you can use C. And if you fail the test, Visual Basic. Whoa. Oh, I'm sorry, it has a grammar now. Never mind, right? It used to be, what does the interpreter think today? I don't know. That's one bug in the bug parade. Bug number 2 in the bug parade, and a bug that's even more important than the buffer overflow, has to do with time and state. Everything that you learned in operating system class about race conditions and lockout and starvation and timeout and all that jazz and semaphores and critical sections, all that stuff is super important. And every single piece of code that we write today, like if you use Java, guess what? Java's multi-threaded. So you get a Java guy in for an interview and you go, do you know how to write reentrant code? And they go, re-who? And you go, do you know what reentrant means? They go, re-who? And then you hire them anyway, right? So the problem is best shown graphically. Here's the blue stuff that we need to get done in one atomic operation, and instead we divide it into 3 things, and a clever attacker can change the state in between the things. And the problem in computer science and in programming is when we think about programs as humans, generally speaking, we think, well, here I am at step 1, and then I do this, and then I set A to 4, and then I go from 1 to A, do some stuff, and you do a little loop and whatever, and then and you think it's like one thing at a time, right? But what really happens on a computer these days is you do step 1, and then the entire world changes. And then you do step 2. As if step 1 might still be valid. Well, is it? That's a really good question. And if it isn't, you can be completely, totally hosed. And we seem to have all sorts of problems like this. I don't know if I'm going to talk about one later on, but time and state, woo, that's a biggie. All right. Now, I got into this with the whole Java security stuff. You might remember there was a little mascot named Duke, right? Here's Duke having a little suicidal issue. So sad. So we discovered a whole series of problems in Java. This is like a little list of all of there, and they all got fixed and everything, and we wrote a book about them in order for people to understand this is the kind of bugs that really good people actually make in their design, and maybe you should go eradicate those bugs in your own code pile. And you know what was weird? You guys remember that Java security bug that happened, 3 months ago? It got all the news. We looked at that, and it was like, whoa, doo doo. Is that how it goes? Doo. You guys are too young. Wow. That used to mean something, really. Time warp. It seems like the mid-90s. There are some problems in the current version of Java, which is, of course, made by Oracle, who doesn't know what they're doing. And, although you should definitely base your class finding system on Oracle, I'm pretty sure that. That's your fault. Right, so deja vu means we've got these same problems cropping up again in the Java virtual machine that look exactly like the ones from the mid-90s, and that's sort of bad. I wish we'd learned something about that. Then there's the modern bugs. Everybody knows SQL's a database thing, and there's just database language, and you do some queries, and blah, 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 and they can be in code, and yada, yada, yada. And some people think this is the most important bug on earth because, I don't know, they're clueless, right? So here's one of my favorite SQL stories. We had a competitor who had one of our current customers as a customer, and they said, hey, the customer said, hey, will you guys do a review of the security of this system? And they said, oh, yeah, we'll do it. So the competitor did a review, and they said to the customer, who's now their ex-customer, we did a review, and we got some good news. You have no SQL injection vulnerabilities in this system at all. And the customer said, we don't have a database. You're fired. Right? Really? And now they're our customer, right? So don't look for SQL injection bugs in code that doesn't have a database. And be all excited when it's not there. Okay, that would be helpful. There's still consultants that get away with that nonsense, right? There's cross-site scripting. That's another one, flavor of the day. There are millions of these things. And the problem is, there are millions of these things. It's a sort of an endless parade. And what we really need to do is figure out a way to glob these things into categories. So when I was writing software security, I got together with Brian Chess and a couple of other people, and we sat around and we tried to make 7 or so categories. Now, why 7? Well, because that's how many people can remember. That was our constraint. Our constraint was 7 plus or minus 2. Really? And so we came up with 8. Right? And there they are. And it took some bulldozing and some baloney and some squinting and standing way back. But listen, if we're going to come up with a science about vulnerabilities and bugs, we need to think like biologists here. What we have in computer security and in software security in particular is a lot of people who want to explain this particular bug in that piece of code right there. And there's no way to generalize from that. So when we were talking about exploiting software today, part of the challenge of writing that book was figuring out how to pile up the bugs into categories which we called attack patterns in that book. But there are categories of bugs that you can think about like this. We called them the kingdoms because we were trying to echo biology, right? So the idea was these are the kingdoms, they're the ones at the top. And if you think about all of these categories, instead of just thinking about a particular bug or God knows 10,000 particular bugs, maybe you'll make some more progress, right? So here's what I really think about the bug parade. Now let's talk about why. We can actually get rid of bugs because bugs are syntactical, generally speaking, and they're not so distributed, generally speaking, and there they are in the code on line 42. So you can go, oh look, get s. I shouldn't have that in there. And you can even grep for get s, which is great unless you use something like father begets son as a method because it has get s in the middle, so whatever. Or, you put in a comment that says don't use get s or I didn't use get s. Really, grep will be like, dude, get s. I know, come on. So we have to be a little bit clever about how we look for things. Grep's not so good. There are better ways to do this. We can build an abstract syntax tree and we can slide around looking for bugs in that syntax tree, and that's good. But that solves about half the problem because there are two kinds of defects in the world. There are bugs and there are flaws. If you had to divide up bugs and flaws into percentages of the defect pile, what would your division be? Anybody have a guess? Yeah. 15% bugs, 85% flaws. Wrong, but a good guess. Anybody else? 80-20 which way? Oh, you two are going to have to fight it out. Yeah. Yep. Also wrong, but interesting. Well, we have a mathematician in the audience. I heard you say that earlier, but I ignored you. 50-50, 50-50. Going once, going twice. Oh, that is correct. 50-50. My favorite answer of all time to a quiz that I did like this out in California once, some guy said, 70-70. And everybody said, whoa, he should not have a compiler. They moved away from him slowly. Yeah, it was C++, right? So it was in the SDL. So really, maybe the guy was right after all. Maybe there were 40% more than we thought. I don't know, but I got to tell you this. When you're solving the software security problem, realize that security is not just about bugs and the bug parade. Sure, we got to get rid of bugs. Sure, we got to find those. Let's do that with some automated technology, but let's realize that that'll solve just about how much of the problem? No, 70%. My God, All right. So I've been talking about software security for about 10 years, and we have 250 people at Cigital. So a couple years ago, I started bringing them together for what we call a technology fair. And the idea is, the guys in New York, they think they're better than the guys in Silicon Valley at something like code review. And you get them all together, and they realize that we're all actually pretty good, and maybe we can learn from each other and kumbaya and all that jazz, right? So I always give a big talk for that, and I put my slides together a couple years ago, and I showed them to my boss, the CEO, and he looked at him, he goes, dude, that's what you say all the time. You can't say that again. And I said, I have to say that again. He said, no, you can't say that again. Like, I have to say that again until I'm dead. Really. I mean, this is just barely getting started. We have to make sure we don't forget the obvious stuff. So I had to come up with a clever way of presenting the same old crap, and so I used zombies, right? And these are ideas that should never die. They should just eat your brains, okay? So here are the zombies right here. We'll go over them real quick. Network security doesn't work. Sorry. More code, more bugs, SDLC, bugs and flaws, and bad dishonor. So let's talk about those zombies real quick. Number one, perimeter security. Now that would be really cool. It's an excellent paradigm if we had a perimeter. Right? What happened to the perimeter? Well, it disappeared, right? So now we're having massively distributed systems, and finding the perimeter is hard. And if you don't have a perimeter, how the heck are you going to do perimeter security? Like, where do you stick the firewall? I really don't know, because there's not really an edge. Like, do you stick a firewall between yourself and your cloud provider? If so, why? So, these are things we got to think about. And then it gets worse. So if you ask a typical set of developers, what do you guys think security is? First they point over there. And then they say, well, we're pretty sure it's a thing. What do you think the thing is? Close. It's a certain kind of technology. Anybody? Cryptography. Cryptography. Exactly right. They go, yeah, it's secure because we added SSL. Yeah. And the idea is if you just sprinkle magic crypto fairy dust everywhere, surely it'll be secure. Surely. Now, why would people who build stuff for a living think that? The reason is we've been training them for years to think about software as features and functions, and to think about their planning in terms of features and functions and how long it's going to take and how much it's going to cost. And so naturally, when you go to them and you say security, they go, well, that must be a feature, and I know one called crypto, so let's just pretend it's that, right? And we have to tell those guys, look, security is not a thing. We can use those things to try to get some security properties, but security is a property. It's kind of like quality. Wouldn't it be cool if you could just like select quality and check the check box? Why can't we do that? We can do that with security. Yeah, I'll turn security on. Yeah, wrong. Yeah, wrong. So that's bad. And then there's so override security function. Then there's the worst thing of all, reviewing products when they're complete. So imagine you're from security and you're here to help. And you go talk to the developers and you're like, yes, we just did a security test that you didn't know was coming, and we like broke your stuff, and so you can't ship it, and you suck. And they're like, who are you again? Security, and you suck. Seriously, that's what we do. It's like the first time you meet somebody, you throw a rock at their face. And then you wonder why they hate you. Because they thought they were done and they were getting ready to ship, right? And you said that they suck. It's like calling somebody's baby ugly. Never. Don't do that. No, don't even try to spin it. Like you can't say, oh, those 3 arms will come in handy. You know, no spin. That's just when you be quiet, right? So I know that's beyond the pale, but that's okay. It was amusing. So we have to figure out a way to engage with developers that doesn't involve telling them they suck or throwing rocks at them, you know, and trying to teach them how to do the right thing. Here's the good news. Developers actually, by and large, want to do things right. They just don't know how. So if we teach them how, then their natural propensity to want to do things right will get them to do some stuff right. And that's something that we can realize. So we got to fix that insecurity, and probably the worst way of doing this by far is penetration testing. So penetration testing works like this in the real world. You hire some reformed hackers, and you know they're reformed because they told you that they were reformed. And you give them 2 weeks to do a system analysis for 20K or whatever, and they find 6 bugs. And they tell you about 4 of them. And you figure out you have enough time to fix 2 of them, so you fix those 2, and then, yay, done. That's how penetration testing really works in the real world. That's one problem with it. So that leaves a whole bunch of bugs, the ones that they didn't tell us about, plus the 2 they did tell us about and we couldn't fix anyway, still in the bug pile. And it gets worse. How much does it cost to fix a bug when you're done? A lot. Remember that study from Barry Baum that we've all been citing since 1972? I'm so sick of that work, right? I asked Barry if he would please just do a new version, and instead he's doing Kokomo or Schmokomo or something like that. I don't know. And you know, so we're all relying on that, but guess what? That study was right. It cost about 1,500 times more to fix a bug in production when the thing's already shipped, or maybe more if you just lost control and you shipped it to 40 million people. Than it costs when you're thinking about the problem. And you get your thinking wrong and you fix your thinking, guess how much that costs? 0, maybe 1, right? So we need to do thinking about security way earlier in the life cycle, and the idea of penetration testing is not so good for that. Since it's late, it's economically silly. All right, that's one thing. Another thing, more code, more bugs. You can go to any development group on Earth and you can say, who's planning on having more code at the end of the quarter? They're all like, yeah, me, ooh, we get paid to make that. Ooh. Really? And then you say, Well, who's planning on having more bugs at the end of the quarter? So let me get this straight. You guys are going to have lots more code and no more bugs. Yeah, you're on crack. The fact of the matter is that if you have more code, you're going to have more bugs. And in fact, the data back this up. Dan Gear, this is Dan Gear and this is not Dan Gear, wrote a paper that got him fired from at stake about Microsoft being a danger to national security because they had a monopoly grip on the market and their software was broken. And the funny thing was, at stake's biggest customer was Microsoft. So guess how long Dan's job lasted? Like 15 seconds, we were all waiting for the phone to ring. Ring! Hello, Redmond, yes? Can you fire Gear? Okay, you're fired. So he knew he was going to get fired, right? But he had in his paper this prediction that the more code, the more bugs. And I said, oh yeah, well here's the data. So I gave him the data about the number of bugs tracked by CERT up through 2007. And I also got data about the Windows code pile, which was like pulling teeth. But here's the Windows code pile over time up to XP. 2.5 million lines in 1990. XP was 40 million lines. Windows Vista doesn't really matter because nobody uses it. And Windows 8 is something like 8 trillion lines, right? So, because it does some stuff. It does tiles and stuff. Tiles. Some stuff. It's cool. It's like squares are cool again. It's the 50s. Bad. Green text, yeah. ADM5s for you, right? So I gave these data to Dan, and I said, what do you think? And you know what? You should never give actual data to people with a PhD in biostatistics because he made these things correlate like you would not believe, which is in Chapter 1 of Software Security. You can read that if you want. But suffice it to say, more code, more bugs. Now, there is a subtle message here. And I spoke about this earlier with a little small batch of students, but I'll repeat myself here. So, we're getting better at software security. And the defect density ratio is dropping over time in terms of KLOC. And you can see that in actual measurements made by Microsoft and others. I'm sure you do that work all the time. So the defect density ratio is going down. That is, bugs per square inch going down. The problem is that we're building more square miles of code every day than we ever made before in the history of the planet. So the bug pile appears to be growing even though we're getting better at it in little globs of 1,000 lines. Everybody see that? It's got 2 whole variables, which is way too hard for technology analysts to grasp. So they say, well, all the stuff the software security guys are doing doesn't work because there's more bugs than ever. And you just go, oh my God, you're so dumb. Stop telling people what to do, right? But we're making progress, and the defect density ratio is going down. Okay. Next, zombie. You should put software security activities into your software development lifecycle, right? There are many firms that think they have a software development lifecycle, short of Microsoft, who are fascist, and they kill people and fire them if they do not use the special SDLC. Everybody else has 25 million SDLCs. My favorite is when there's a department of bureaucracy who believes there's one. Like at EMC. We talked to the Department of Bureaucracy, and they're like, oh yes, everybody follows the one special thing. Here, it's all written down in this piece of paper. And you go over to Dev, and you go, you guys use any of that crap? And they go, no. No, when they come with a clipboard, we just say, oh, yes, 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 yes. Oh, yes, 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 we did some testing. We did it. And the people with the clipboard from software bureaucracy, they're too stupid to ask for results. So they're like, oh, testing good, check. And then you're done. And instead, there are 40 SDLCs, maybe every single possible SDLC. Let's name a few. Well, there's Agile. There's extremely bad programming, which is related to Agile. There's Scrummy, Scrum. There's the spiral thingy. There's a waterfall one. Let's see. There's Tim's way. That's the best way. If you want a bonus, Tim. Work for Tim's group. Tim always ships. Tim gets a bonus. Tim's way is the way. You'll find Tim's way in every corporation. So the thing is, you have to come up with a way to describe software security activities that fit in no matter what the SDLC is. That's what I talk about in the touch points, which is similar to the stuff that is in Microsoft's SDL, but Microsoft's SDL assumes that you're using an SDLC, which is incorrect. And you should never, ever go to a dev group and say, well, you guys, I know that you do Agile Scrummy Scrum Scrum, but you really should switch to CMM level 53 and use UML. They'll be like, okay, I quit. That's what really happens, right? So you can't come from security and go, well, you guys are going to have to change your entire SDLC because I have a better one. They'll be like, okay, I quit, and get another job next door where they don't have an SDLC. Okay, bugs and flaws. We already did the bugs and flaws thing. What's the division there? Middle guy? Division between bugs and flaws? 70-70. Still not paying attention. Bad. All right, so that's another zombie. Here's another zombie. This one's really important. And testing people know this, and we need to tell the non-geeks and the normals out there that this is the way this stuff works. Imagine that you took a hacker and you put the hacker in a can, right? So who's the hacker? We put XF in a can or whatever. And the canned test can be run against any arbitrary program. Let's call it program A. So you run the can against program A, and the program gets hacked by the can. Like can test, hack program A. What do you know about program A? It sucks. That's exactly right. That's a technical term, and it's an important one. Yes, can test, broke your code sucks. Go back and do it again. So imagine that you run the same can test, because there's only one can, against program B, and it doesn't find any problems. What do you know about program B? Not nothing. Who said nothing? That's wrong. No, it's epsilon. You know epsilon, right? So you know that you ran some tests and it didn't fail those tests. It's a smidgen, but it's better than it's not nothing. Now, what you have is a badnessometer. It's not a security meter. It's a badnessometer, and it goes all the way from your code fell prey to the can test, so your code sucks and you're in deep trouble, all the way to we ran some tests and didn't find anything, so we don't know. Now, I dare you to find any security people that go, we don't know. We did some testing. We didn't find anything, so who knows? You know what they say? Well, we hired some reformed hackers, and they found 2, and we fixed them, right? So, never forget that badnessometers are badnessometers and not security meters. And watch out for when you go get your job out of school, there's going to be some dingbat VP who wants to treat a black box testing tool as a security meter. That guy is wrong. Okay, those are the normal zombies. Now I have one extra zombie for you. This is a zombie baby. I gave this talk in Argentina just a couple of weeks ago, and there was this woman in the front row who was pregnant, and it was like, ooh, not your baby, not your, not your baby. It was really rather awkward. We spend a lot of time in security and in software security talking about what's the best way to find bugs. My way is better than your way. We should do static. No, we should do dynamic. We should do hybrid glass house upside down left-handed bottle washing static. No, and there's a lot of argument over what's the best way. Let me tell you the truth of the matter, you guys. It doesn't matter what the best way is. We already have too many bugs. They're already in the pile. And if we don't fix the damn bugs, who cares if we find more? Right? You go anywhere on Earth, and the bug pile for security is still large, and they need to be fixed. And we're all arguing in software security land about how to find more. How about if we instead figure out how to fix the ones we already know about? Now, we spend a lot of time at Cigital fixing stuff, because if you find bugs and you don't fix them, you are part of the problem. You're not part of the solution. And we need the solution done, which is actually fix the dang software. And so that's the zombie baby. You'll hear me saying that a lot for the next 10 years. Okay, touch points we sort of already talked about. Remember at the beginning of the talk where we had the security people and the development people and nobody in the middle? Nobody has been replaced by the software security group. Every firm that does a software security initiative in a reasonable fashion has a software security group. And the software security group does software security all day. I'm going to tell you about a study that studies the work of 1,000 people who full-time do software security on planet Earth for 51 different firms. That's full-time software security people, and they have a boss who runs the software security group. Sometimes it's called the product security group. Sometimes it's called application security group. Doesn't really matter, but there's one of these in each one. If you figure out how to be a productive member of a software security group, you will have a job for the next 30 years, guaranteed. And you'll get paid a ton of money, guaranteed. Right? So we all know about this SDLC thing. You should buy my book instead of Microsoft's. That's the only point of that slide. And here's why. Because there are multiple SDLCs, so we have to focus on artifacts instead of process. And if we look at artifacts and we put little boxes counting as the artifacts, there's the standard issue artifacts no matter what your SDLC is. Then we can figure out what to associate with those artifacts when we have them. What's the one artifact in those boxes up there that should be associated with every single software project? Read the boxes. Code. Who said code? That is right. There are some government projects that don't have code yet. But they're going to have code any day. Any day. Any day. Now, the good news is, in software land, there's usually code. So if you have some code, then you do code review with a tool. Yay! There are tools for that. They're pretty good. They're a lot better than they used to be. They're not perfect, but they sure beat code review by hand. Right? Yes, they do. Yes, they do, because we suffer from the get done, go home phenomenon when we're doing it by hand. Right? What's the second most important artifact up there on that list? Architecture and design. And here's how it goes. We used to get calls back in the early 2000s. People would go, hey, you guys, you do architecture analysis, don't you? We said, yes. Well, how much does it cost? We said, well, it sort of depends on what you built. Can you send us your spec? And they would go, yeah, we were going to write that down. And we would go, doo-doo-doo, the number you have called is no longer in service. No, we would go, all right, we'll come help you reverse out your architecture, because you can't do an architecture analysis unless you have an architecture or a spec. Now, here's the dirty little secret of software. The dirty little secret. If you don't have a spec, your code cannot be wrong. It can only be surprising. Oh. So when you go to a coding group and they don't have a spec, well, they can't be wrong, right? Do you think they're going to want to get a spec? No, because then they might screw up. Seriously. So it's sometimes as simple as that. I like to do a one-page overview of a system, and sometimes they don't exist and you have to build them. And the most valuable part of the analysis is the one-page overview, where you can look at the forest instead of looking at all the trees, which security tends to do. All right, in the last 10 minutes, I'm going to talk to you, or 15 or something, I'm going to talk to you about what we're doing to measure software security initiatives. So here's a little story about how this project got started 4 years ago. I was at a technical advisory board meeting at Fortify. I chaired their technical advisory board, and we had one of the Fortify guys present yet another software security methodology. This was going to be the one that Fortify was going to use for all their customers, which is a rather silly idea. And so this guy presented a fairly reasonable thing based on the experience of working in one firm. So it was a one-dot generalization. And if you know who Fred Schneider is from Cornell, Fred was in the room. And you know, Fred has this way of asking a question that like somehow takes all the skin off of the questioner, and the skin is like laying around their ankles, and they're trying to think about Fred's question with their skin around their ankles, and all of a sudden they realize they've just bled to death. Well, so Fred was doing the Fred thing, and I stepped in. I was like, oh, don't kill the guy. He's just a kid. Well, I think maybe what we should do is, instead of talking about yet another software security methodology, because we've got the touch points, we got SDL, we got class, we got element OP, why don't we go out and gather data from real firms and then describe what we see in a model based on the actual data? We'll call it science, right? So we decided that would be a good thing to do. And so I called up 10 of my friends, and I'm like, dude, we're going to do some science. So I call up Lipner at Microsoft, going to do some science. We're going to measure some stuff. We're gathering data. He's like, I'm in. So we went out there, and we gathered some data at Microsoft. We did it at, I don't know, Goldman Sachs, at Fidelity, a few other places, 10 places. 10 places where I knew they did a reasonable job with software security because I was either helping them or I'd known them for 15 years and I trusted these guys, and we were trying hard to build a descriptive model. Well, 4 years later, we have 51 firms. Actually, there are 58 now. 51 in BSIM 4, which was released in September. There are now over 100 measurements. At the time we released BSIM 4, there were 95. So how can there be 51 firms and 95 measurements? And the answer is some firms are measured twice. One firm's been measured 3 times. Some firms are so big that we have to measure their subparts and then roll them up into one score, and that counts as one firm. For example, Bank of America is one firm, and they have this small little division called Merrill Lynch, and another one called Countrywide, which they really shouldn't have, but they have it, so they're stuck with it. And, you know, we measured them separately and rolled that into one. So we've gathered a whole bunch of data, and we've published those data for free. Here are the firms that we gathered the data from. See if you recognize any of these, right? So, biggest software firms on earth? Yeah, probably. The 3 biggest are there. Biggest banks on earth? We got JP Morgan Chase, we got Bank of America, we got Wells Fargo. People doing hardcore new stuff? Well, how about these guys? This is pretty darn hardcore new stuff. How about Cloudy Cloud? Oh yeah, we got some Salesforce dudes. There's the Box guys. Nobody's even heard of them yet, you know. So we even have some Germans. Look, the Germans are up there. And my favorite of all is Intel, whose name we can use, but we can't use their logo. So I invented a new logo for Intel myself called Times New Roman. It's pretty cool, huh? And then there's some chicken firms, 17 chicken firms who don't want us to out them, and I couldn't tell you, like, no, I shouldn't out them. All right, so here's the idea behind this work. The idea is not to tell you what you should do, but rather tell you what they're doing. So we go out into the jungle, and we went to 51 jungles, and we go, oh, look, in this jungle, monkeys eat bananas. And in that jungle, monkeys eat bananas. This jungle, monkeys eat bananas. And in fact, in 38 out of 51 jungles studied so far, monkeys eat bananas. What? Does that mean monkeys should eat bananas? I don't know. That just means monkeys eat bananas in 38 out of 51 jungles, right? So what we're talking about is a descriptive model. It's not prescriptive. It does not say, do not run while eating bananas. It does not say, only eat yellow bananas. And it does not say, thou shalt not steal thy neighbor's bananas. It says none of those things. Instead, what it says is a whole bunch of facts. Now, the thing is, it's hard to argue with facts. And the interesting thing about the BSIM is there's a whole ton of facts. And so if you have a theory about software security, go check our data and see whether it holds with the data. And if you believe that the firms that we've studied are not full of complete idiots, which is debatable, then maybe those data will be useful. But guess what? There's data. The data is published. The data is tracked over time. We have a consistent way of measuring the data. Let me say this one more time. There's data. We have a measurement for software security. Now, the measurement is not we took some software and we stuck it in a box and the box either turned red or green. There's a problem with that box. You know what that is? Can't exist. Anybody heard of the halting problem? Right. Apparently there's some security vendors who have not. If someone would please let them know about the halting problem, that would be helpful. Now, we gathered up all these data and we crammed them into these little boxes. There are 12 boxes here called the Software Security Framework, and those boxes are kind of like an archaeological dig. You know when you go to archaeology land and you put a little stake in the sand and then you put a little string and then you say, well, look, in square number 4 we found like what do you find in the United States? We found an Indian head, right, an arrowhead. And if you're in Europe, we found like a piece of metal from Rome, right? So those are the 2 things that you find, and you just describe which square you find those things in. We have identified 111 activities, and we divided them into these 12 squares. For example, architecture analysis has these activities that we have observed in it. There are 1, 2, 3, 4, 5, 6, 7. There are 9 activities. Why are there 9? There are 9 activities, right? Now, if this were some sort of theoretically perfect model, there would be 120 activities, and they would fit nicely into the 12. There would be 10 for each, and blah, 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 blah. That's not how it works. Some practices have a lot of activities, and some have not very lot, right? we divided those further into 3 levels. Level 1 stuff, super easy. Level 2 stuff, kind of harder, because sometimes you got to do level 1 stuff before you can do the level 2 stuff. Has nothing to do with the CMM levels, by the way. And level 3, rocket science. Really? So, if you were out looking for stuff, how often do you think you'd see the level 1 stuff? Oh, pretty often, because that's easy. How about rocket science? Oh, not very often, because that's hard. And that's the way the data are organized. And we've run statistical analysis against our model since we hit 30 firms long ago. Now, to give you an idea about the intensity of this model, you can download the model for free at bsim.com. Elvis has downloaded many, many versions, and Bill Gates has done a surprisingly large number downloads, or people who call themselves Bill Gates. So each of those 111 activities has a paragraph associated with it, and the paragraph has real examples. This is not a theory. This is a description of 2 or 3 ways that we saw this activity carried out in particular firms. We don't out the firm names, but we could. But I just want to make clear this is real data. The observations are based on descriptions that look like this. We've done it for 4 years, and we have a whole ton of data. And we actually got some accidental side effect data like this. We said, well, how long you guys been doing that? And here's the average, 5.5 years. So you don't just sort of do software security and done, right? Oh, bought a tool for that, check. That's not how it works. It takes a long time. Everybody has a software security group. The smallest has 1 poor guy. But that development group has only 11 people. And you can do some interesting things. You can divide up those numbers, and you can say, in our population, the average of averages, that is, if we take the 2 vectors, SSG size and development group size, and we put them together and we don't roll them up first, and we do the math, the average is 2 software security guys for every developer, 100 developers. Let me say it again. 1 person for every 50 developers. How about that? Now, is that good? I don't know. Is that right? It's right. Is that what it should be? I don't know. That's what it is. That's just the fact. Sorry, I know the Republicans don't let us use those anymore. But it's, oops, that just slipped out. But imagine that we're using facts in science and stuff, right? Okay, so we can count up the number of times these activities have been found among the 51 firms, and we can divide those into the 111 things, and we can come up with a chart like this. So here's all 111 activities, and you see the 12 chunks. Those are the 12 practices, and we can say, for example, this particular activity was observed 45 times out of 51. Wow, that's a lot, right? So we know which things are popular. We know who does what, and we just let you take a look. And you can decide whether it's important to you that 45 out of 51 firms do that activity and you don't, or not. It's your call. And in fact, we can do a measurement and compare you to the world population, or we can compare you to a subpopulation, right? So I just was at NASDAQ on Wednesday and showed them their BSIM measurement and compared them to 19 other financial services organizations. And I was sitting with Mark Graff, who's the new CISO over there, and we were talking about budgets for next year, and he said, damn, I'm taking this chart into budget land because now I know I'm going to spend stuff on. Bing! Mission accomplished, right? So this is a good thing. You can measure these measurements over time, and you can notice things like, oh, look, spiky not round, or something like that. Or, oh, look, we seem to need to do some work in policy and compliance because we're way behind the curve there, and we're way behind the curve in architecture analysis. Of course, that's a very low resolution graph right there because we do it with what we call the high watermark thing. We can do a high resolution graph too. Look at this. There's a little 1 if you do the activity. Otherwise, there's a blank. And remember those things that are really popular, like this one here? 45 firms, don't do it. Does that mean that firm should do it? No. It means they don't, and everybody else does. Remember when your mom said, just because everybody else is going to the mall by themselves doesn't mean you can. Your mom was right, right? Remember that guy who got arrested? That was not you, right? So sometimes mom is right. This doesn't mean you should do it. This is just data. In fact, this whole little chart with all the special colors and everything, it was done with this amazing tool called Excel, right? And Excel is pretty stupid. Excel is not a strategy. This is just data. You take these data, you drive your strategy with the data, then you have a smart strategy, and you have a measurement tool. So there are some firms like Fidelity has used the BSIM for 3 years to measure their software security initiative and adjust it and figure out how to make investments and where they're behind and where they're ahead and what they want to do next year, and it's working like crazy for them, which is kind of cool. So this is a little science experiment that accidentally escaped the test tube. We started with 10, now we got 51. Actually, we got more like 60, shooting for 75. It says 60, but we've already hit that, so now it's 75. My guys don't know that yet, though. And we've translated it into German and Italian. There's somebody working on Portuguese, and I think there's a Japanese version that may never get done. But we're going to collect more data, and guess what happens? When we collect enough data, we go back and we fix the model. Because the model is describing the data and not the other way around. So we did data first, model second, adjust the model, use math, use statistical modeling techniques to actually make the model super tight, and the thing works like crazy. It's a beautiful measurement tool. I would encourage you to steal that work. Now in the remaining 34 seconds, because that's what I've got to hit an hour, I'm going to tell you where to learn more. I write a column for Search Security, and this month's column is about cyber war. I'm in the middle of debates in Washington about whether we should spend more on defense and less on offense when it comes to cyber weaponry. And unfortunately, the people in Washington are thoroughly confused about this. But my belief is that we live in a glass house, and so we should stop working on fast, accurate rock throwing, right? And instead make our house less glassy. We have a blog. Everybody else has a blog, but ours has a cool name. I have this podcast. It has about 10,000 listeners called Silver Bullet. Who's the current one? Oh, we're just going to release one today. I think it just got released maybe 10 minutes ago. And who did I do? Oh, and it's Thomas Ridd from King's College London. Yes. I will give the slides to the dean, and the dean will somehow miraculously make them appear in all of your email inboxes. Or maybe he'll put it on that Oracle system. No, never mind. There's this magazine called Security and Privacy. It's good because it's peer-reviewed, and some of the articles are even reasonably scientific, but on occasion, they may apply to the real world. It's a very small sliver, but this magazine seems to hit that sliver more often than most. I'm sure that you guys have an electronic subscription to the IEEE library, so that's for free. The dean said he would buy everyone in this room a copy of the book, so just ask him later. Is that wrong? And now I'm done. Thank you very much. We have time for -7 questions. So who's got one? Anybody want to break the ice? We've got mics we want to run to you. Over here, right behind you, mic coming.
So just from a methodology.
Talk really loud.
So just from a methodology perspective, how are you collecting the data for this model?
Right. So the data has been collected by the 3 people who built the model: me and Sammy and a guy named Jacob West. And every single measurement activity takes a team of an odd-numbered team, usually 3, to do a set of in-person interviews, and we also look at various artifacts, and then we go and we have about a 2-week fight over what we observed, and then we show the measurement to the people. So the only way that it's objective is by having the same measurers doing it the same way all the time, and we've never let the cat out of the bag. I'm sure that one day KPMG will be using the BSIM incorrectly, so what can I tell you? Right, but right now, we're very concerned about data consistency. And I got to tell you this other thing. I'm a software guy, and I'm like an anti-process guy if you've known me for years. And I used to have huge raging battles with Watts Humphreys, like on stage, and we would yell at each other and stuff. And here, I built a process thing that describes activities. It's really very distressing for me. Very distressing.
Here.
Yeah.
You were talking about more code, more bugs. Do you want to address the myth or abuse of code reuse?
Well, code reuse can be kind of helpful, and one of the activities in the BSIM involves building middleware that's secure for some of your developers to use, so that instead of running out and doing their own implementation of how to do OpenSSL and screwing it up again, you say, well, when you're going to use OpenSSL, use it like this. Here's some code, steal this code. If the code that you're providing doesn't suck, then you will have made some progress. But if the code that you're providing is broken, then you will have introduced a single point of failure into all of your systems. And so, or if it's misapplied, and it goes both ways. And you know what Ross Anderson said about distributed computation. Maybe that was Les Lamport, I can't remember. Well, I guess Lamport said a distributed system is one in which a computer you didn't even know it existed could screw up your entire system. And Ross said programming a distributed system and a computer in a distributed system is like programming Satan's computer. Both are right? And so, you know, we can't provide perfect code to everybody all the time, and they will misapply our stuff. But if we do it carefully, it seems to be an activity some people have found use for. Fair enough? Okay. Who else? Don't be shy. It's not all bad. It can be good.
I know the first principle of security is never assume secrecy.
Yes.
All right, secrecy is terrible. On the other hand, by publishing this, aren't you, in some sense, giving a broad audience attack vectors?
Yes. Welcome to planet Earth. Yeah. I think it's okay to do that. In fact, I was at a meeting in Washington where, you know, I thought we'd done with this debate long ago, and this is more about activities, so it's not really so dangerous, although it might help you think, well, they secured it that way. They're using, you know, Gothic arches or whatever, so we can attack those. But I was at a meeting in Washington of, you know, they've been talking about software assurance for 8 years in a row. They have the same meeting every 6 months, and so far I don't think they've done a damn thing. But they have good meetings. And so somebody was presenting the CVE or the CWE or the element OP, whatever, what's it called? CWE? CWE. And gave a pretty good talk about this bug collection that they built over at MITRE, and they put it up for free, and you can use it if you want. It's a disorganized mess, but there's a lot of bugs in it. And a questioner went up to the mic and said, well, I think it's real dangerous to publish them bugs because Al-Qaeda's going to use them bugs against us. And you're just like, oh my God, take the mic away. Seriously. Seriously. So my belief is this. If you want to know how to fix your systems, you damn well better know how they're going to be attacked. We have to talk about attacks. We have to talk about exploits, and we need to publish them, and that Sunlight is the only way to solve this problem. Who else? Are we done? One more.
So with your bug parade, you mentioned these sort of well-known bugs, buffer overflow, SQL injection.
Yeah.
We're known about these bugs for ages.
Yeah, and still we use C.
So yeah, the question is what can be done, because we're still seeing software with the same old well-known bugs. If we already know about the problem and it's not being fixed, what else is there to do?
What department are you in?
Computer science.
Are you a professor?
Yes.
Are you in theory?
Yes.
Here's a challenge for you. So, got him. Could tell. Theory guys, they stick out. Right? So imagine that you spent since the 40s trying to figure out how to make a universal computer and describe it with, you know, grammars and a Turing machine model. And then imagine that you decided that this thing could compute a lot of stuff. And then imagine that you used it to compute a lot of stuff, and it computed some stuff you didn't want computed. Damn it. The question is, why does it compute that stuff anyway? So is there a way that we can shrink wrap things down so we can have a theory of a machine that might not have universal power, but that can compute less and can't compute the things we don't want to compute? Does that sound hard? Good. Work on that. Yeah. I think we're done. Thank you.